Hello, everybody. Welcome to another episode of Porous Media Tea Time Talks, a part of Young Academy from Interpor. We give young researchers the possibility to present their own research to a broader audience. I'm joined here today by Catherine Spirin from Stanford University and Marcel Mura from PoreLab Norway. And today we have two presentations, one from Olivier Vincent and one from Ting Xiao. And we'll start with a presentation from Olivier Vincent. He's a research scientist at the Institute for Light and Matter at CNRS in Lyon, France. His interests revolve around phase transitions and transport involving water in nanoscale confinement. With that, I'd like to give the word to Olivier for his presentation.
Thanks. So thanks, Ariane, for the introduction, and thanks for the invitation to this nice event. So today I'm going to talk about humidity-triggered filling and emptying of plant-like porous media, so basically artificial trees. It's work I did mostly while I was still at Cornell University in the US, but I'm continuing similar things in Lyon in my group at the moment. So trees are basically very tall porous media. They actually have a very peculiar structure as well, which is they combine nanopores and microscale or even macroscale features. And actually the water coming up in a tree is transported through tubes that are segmented. So they are tubes connected to one another through these membranes that are nanoporous. And the role of these nanoporous membranes is to prevent spreading of bubbles if bubbles form. And I'll show how bubbles form later in the talk and why bubbles form. So that's one of the roles of nanoporous membranes in a tree, but also there's another very important role, which is that evaporation of the water that comes up in a tree at the leaf level actually generates very large suction forces for the water to go up in a tree. And that's a very important aspect of water transport in a tree. And in this talk, I'm going to show a little bit how that works, but mostly through experiments with artificial structures that mimic the way of transporting water that real trees have. And also, I'll show you how we can manage the filling state of tree-like structures by just changing the humidity around these types of porous media. So what I'm going to show here is basically what I would call the simplest version of an artificial tree that we could think of, and it's something we built in the lab at Cornell. It's basically a sandwich between silicon and glass. It's some 2D microfluidic structures, if you like, but it's very simple. So there's a reservoir on the left filled with water, and there's an open edge on the other side. The only way for the water from the reservoir to exit the system is to flow through this nanoporous layer to the evaporative edge here. And we can see it as an artificial tree because the left part where the reservoir is here, we can see it from the top here, is basically the root part of the system, is where the water will be pumped from. At the other edge here is the leaf part of the system. This is where water evaporates and generates suction forces for the flow in the system. And of course, the water flows from the reservoir to the leaf through what we could call the stem part of the system, which is in this situation just a nanoporous layer. So we can do experiments with this type of structures by just filling them with water, leaving them in some environment with controlled humidity, and look at what happens. Actually, what I show here, every line is an experiment with a different level of relative humidity that we impose on the system. And what we see on each line is the reservoir itself. It's a long channel, and when we do the experiment, we see it empty. And of course, at different levels of relative humidities, we see that the reservoir empties more or less quickly, meaning there's more or less flow in the system. The first conclusion from what we see here is that this little artificial tree works in the sense that we are pumping water from the reservoir to this edge of the system. And what I'm going to explain here is why we have this peculiar relation to the humidity in terms of the flow rate in the system. This is another way to plot the data that I've just shown, which is basically the Darcy velocity, or the velocity of the fluid in the pores as a function of the relative humidity here. 100% relative humidity, fully wet, is on the left part of the graph. And when we go to the right, the air around the sample gets drier. And you can see that if the relative humidity is high enough, we have very linear dependency of the flow on actually the driving force that I will explain later here, but the flow increases when the relative humidity decreases, but at some point it saturates. And the explanation for this is actually relatively simple. If we consider basically what happens at the edge of the system here, where the water evaporates, if we focus on one of these little pores that are in the interface between the liquid and the vapor phase outside, actually we can have an equilibrium of the liquid in the pore with the outside humidity, even if the humidity is not saturated. And this is described by Kelvin equation. And what Kelvin equation entails is that at a given level of relative humidity, there's a given curvature of the meniscus, and the relative humidity controls the curvature of the meniscus. And through Laplace law here, it also controls the capillary force and the capillary pressure at the edge of the system. And this capillary suction force is the force that drives the flow through the system. So when we drop the relative humidity, the curvature increases, and at some point it saturates because the curvature cannot be more than what's allowed by the geometry of the pore. Actually, with these very tiny pores, the curvature can be extremely large, and that means we have also extremely large driving forces. If you look at the values here in terms of the pressure at the edge of the system, we go to about several hundreds of bars of negative pressure that drives the flow. What's interesting is, in addition to the fact that the driving force is massive, it's also tunable with relative humidity. So that's an interesting aspect of these humidity-driven flows through nanopores. A drawback with this very simple tree, though, is that it has very low permeability. It's only nanopores all the way through, so that the permeability is extremely low, as you can see on the value here. And so, of course, trees don't really do this. As I showed at the beginning, trees are not only nanopores from the roots to the leaves, but it's a mix of nanopores and microscale or even larger scale features. And so one of the ways to mimic a bit more what happens in a tree is to move from a system where we have only nanopores to systems where we have a mix of microchannels interconnected by nanopores. Actually, we did this with the system. We could add basically some microscale features, in this case, microchannels in the structure here. And if we do the same experiments as I've shown before, in some situations, we get this type of effects, where you see the channels initially are kind of black, so they mean they're filled with water. But very quickly in the experiment, they empty spontaneously. And the reason for this is that because of the massive negative pressures due to the capillary forces at the edge of the system, we get actually cavitation of the bulk fluid that is contained in these microchannels. So what is cavitation and why does it happen here? It's useful to go back to the phase diagram of water, the thermodynamic phase diagram. We know that if we lower the temperature on water, we can freeze it. If we increase temperature, we can boil it, because we cross the liquid vapor phase transition line here, but we can cross the same line by decreasing the pressure instead of increasing the temperature. And when we do this, that's what we call cavitation. What's interesting, so that's actually cavitation in one of our structures here. It's a very fast and sudden and violent event. What's interesting is that cavitation actually happens typically not at the transition line here, but at very lower pressures, typically pressures that are absolutely negative. In our artificial trees, we estimate that cavitation happens when the pressure in the fluid reaches minus 200 bars. In real trees, actually, it's more moderate negative pressures, but still absolute negative pressures on the order of minus 10 to minus 100 bars. Potentially, the nucleation mechanisms that lead to cavitation in trees is a little bit different than in artificial trees, but I won't discuss these details here. All right, so what we showed with artificial structures that have this combination of micron, let's say microscale features interconnected to one another through nanoporous layers, is that they have cavitation, and the cavitation dynamics is very peculiar because it leads to fronts that are kind of self-organized, where you have bursts of events and then nothing, and then bursts of events and then nothing. And I don't have time here to explain the mechanisms behind this, but it's due to the nonlinear coupling between the pore-elastic relaxations of the pressure field in the system and the stochastic nucleation kinetics. What I want to discuss now is, okay, if we have cavitation in the systems, it means we lose the water that it was contained in the microchannels, and so we lose the water and we lose conductance of these channels. So for a tree, it's not good because it loses its conduction from the water from the roots to the leaves. There are actually questions in the community, in the plant science community, about whether trees can refill after cavitation, and I won't go into this debate here. Some people think it happens in trees, some people think it doesn't. But what I'm going to show here is that we can do it in artificial trees at least. And the solution to this question of how to refill after cavitation comes actually from solutions. And what I mean by this is that we can use a solution, solutes in the water instead of pure water. And if we do this, we can still cavitate the system if we drive it at lower humidities. For example, in 60% relative humidities, things cavitate completely. But once we have cavitated the system, if we have solutes in the system, we can actually refill it by increasing the humidity again. And just by changing the humidity from 60 to 86%, we can refill the system, as you can see on the movie on the right here. So the thing completely refills until there's no bubbles anymore. The reason for this is actually osmotic flows in the system. Due to the interaction of the humidity with the solutes on the edge here, we can create gradients of concentration in the system that can create osmotic flows that refill the system, or actually that can empty it as well. And we can play around with this thing and have fun with it by changing the humidity. Basically, if we go from low to high humidities, we can empty or fill the system reversibly, as I can show in this movie, by changing the driving force, just by changing the humidity, the external humidity we impose on the system as a diode. Okay, so that's what I wanted to show in this short talk. It's actually a combination of different papers that we did that I'm going to show later. But the conclusion of what I wanted to show is that trees have this combination between macro scale features and nanoscale features. The nanoscale features enable massive capillary driving forces through the system, order of hundreds to sometimes thousands of bars. They act as a seal against air propagation, and they also enable osmotic flows to develop in the system. And the macro part of the system in a tree enables large permeabilities so that there is large flows, and actually flows in trees can reach centimeters per second in the summer in large trees. But also they lead to cavitation and embolism, so there's a drawback and a safety trade-off that I didn't talk much about, but trees have ways to protect themselves against cavitation. So in my group right now, I actually investigate other aspects of salt solutions in nanoporous media, and you can learn more by visiting my website here. And just for information, that's the 3 papers corresponding to the 3 parts I've shown in my talk, and this is the funding sources we had for these studies. So I thank you for your attention, and I'm happy to answer any questions.
Super. Thank you very much, Olivier. So if there are any questions from the audience, please write it down on the right side of the screen. I have a quick question to start with. So you showed this walls inside the tree capillary, so they prevent a bubble from growing more than the size of this cell, right?
Exactly.
So this, if I understood correctly, this is a mechanism to stop like the cavitating bubble to just grow and disconnect the whole tube. Yeah. But a liquid under negative pressure, it's on this unstable, this metastable state, right? So any kind of perturbation can cause a tiny bubble to cavitate. So how come the thing that I don't understand is how come trees actually are stable? Like why doesn't the tree just explode if I knock on it like that?
Yeah, so I mean, it's always a question that we have in this context, and it's a good question, and it's actually a question that has had debates for many years in the plant science community. Now, I mean, we're pretty sure that there is actually negative pressures that are sustained over weeks or more. Actually, I mean, the negative pressure decreases at night. Typically, it goes back to 0. And during the day, due to evaporation, it increases in magnitude. But typically, the thing is that water can be metastable for very long times in these negative pressure regimes. And if the negative pressure is not too large in magnitude, it takes forever to cavitate. So it relies on this kinetic stability, but not thermodynamic stability.
Hey, super, thanks. Do you have any other questions from the studio here? I have another quick one, maybe. If we still have time, I think we do. So why was relative humidity the parameter that you chose to tune, and not, like, for instance, like temperature around like in the leaf area?
I mean, humidity is kind of the natural driving forces in these systems because, yeah, that's what happens in a tree, is that it's really the difference in humidity that drives the flow. Of course, actually, temperature has a role, and if there are temperature gradients, it can change a lot the system. But humidity, yeah, it's an easy parameter to change. But temperature gradients are important as well. We could do it with temperature gradients, the same kind of studies. What's important is the chemical potential, basically. So changing humidity or temperature results in the same kind of dynamics if we change chemical potential in the same way, I would say.
It's a lot. And for the audience, I'd like to say also that you can also contact Olivier directly afterwards. So there was a link to his website. I think he left it there in one of the slides. So feel free to contact him afterwards with additional questions if you have. Okay, so I think we can move on to the next speaker now. Thanks a lot, Olivier. So our second speaker for today, it's Ting Xiao, and she is a postdoc researcher at the Energy and Geosciences Institute at the University of Utah. Her research interests include subsurface reactive transport, geologic carbon dioxide sequestration, uncertainty risk assessment, hydrochemomechanical coupling, and underground sources of drinking water. So Ting, welcome to our studio.
Thank you, Marcel, for the introduction, and I'm very appreciated for being invited. Today, I would like to share some of my research on geologic carbon dioxide sequestration and assessment of potential risks of leakage. So as we know that in recent decades, atmospheric CO2 level is higher than ever, and it is growing very fast. Today, CO2 concentration in the atmosphere is about 413 parts per million, and which is much higher than less than 300 ppm in the history. And if we don't control the CO2 emission, CO2 concentration might be 600 ppm in another 50 years. Scientists found that the global temperature is highly related to CO2 level. And if we don't control CO2 emission, global temperature might further grow and cause severe climate change. With the climate change, more severe weather will occur very often, and habitats of human beings and other creatures might largely impacted. So here is one idea of mitigating CO2 emission, which is to capture CO2 from centralized sources, such as power plants, and transport them by pipelines and inject them into deep storage reservoirs, or which is overlaid by an impermeable layer or called caprock. This idea is called carbon dioxide capture and geologic sequestration. One of the largest concerns of geologic sequestration is leakage. Possible leakage pathway can be through wells and or fractures and faults. It is very important for us to know more about leakage risks, including integrity of sealing formations and wells, leakage pathways, and potential leakage impacts on groundwater and or atmosphere. It is a big concern that once a leakage enter an underground source of drinking water, what would happen? Because CO2 is an acid, so possibly it will reduce pH and cause some sediment dissolution. which release a lot of cations, including toxic trace metals. So today I would like to share one of my studies on CO2 groundwater sediment interaction. So our objective is to evaluate this process to influence the shallow groundwater quality and to quantify the mobilization of trace metals. Here is our case study site, the Farnsus unit. The Farnsus unit is located in the northern Texas in the USA. And this is a demonstrative scale CO2 enhanced oil recovery and storage site. CO2 injection started in 2010 from anthropogenic sources. After about 11 years injection, almost 1 million metric tons of net CO2 is stored. The overlying shallow groundwater aquifer of this site is the Oglala aquifer, which is the largest groundwater aquifer in the Northern America. We have many monitoring shallow groundwater monitoring wells to collect water samples routinely. By far, we didn't see any leakage from this site, and these monitoring data are very useful for us to know the background value of the groundwater quality. We collect some sediment samples from about 20 miles from this site. And with the samples, we detect of scanning electron microscopy and X-ray diffraction to determine elements and mineralogy of this sediment. We also did particle size analysis and also acid digestion tests to determine what elements are easy to release under acid conditions. So these elements are of special interest in further analyses. Then we set up several column experiments by injecting CO2-rich synthetic groundwater into the columns, and we collect the effluent water samples. Control experiment was also conducted by nitrogen-rich synthetic groundwater. Here is our experimental design. First of all, we inject nitrogen synthetic groundwater for 3 days to stabilize the system. And then we start to inject CO2 synthetic groundwater into the columns for 30 days. Then we have a 3-day stop injection to extend hydraulic retention time to see if there's any further chemical reactions. Then we resume the injection to the day 42. And after that, we change the injection water to a nitrogen synthetic groundwater to mimic when we fully control the CO2 release and CO2 intrusion is stopped. This period is for another week, so the total experimental time is 49 days. With the water sample, we test pH, cations, anions, and dissolved inorganic carbon. Here are some results and discussion. It's obvious that with CO2 intrusion, pH dropped very quickly in 1 day, and then it decreases to a little more than 6 and keep stable in the later of CO2 injection. With the stop flow, pH doesn't show obvious changes. It suggests the buffering effect of carbonate mineral dissolution is very strong. And after we stop CO2 injection, pH will increase back to the control level in about 1 week. We found 3 patterns of cation dissolution. The first one, such as calcium, shows a quickly increase, and it reaches the peak in about 10 to 14 days. and keep a high level till the end of CO2 injection stops. We interpret that this is due to calcite dissolution because it is a continuous source of calcium release. And to be noticed with a higher flow rate, calcium concentration drops in the later stage of the experiment. We interpret that it is because the loss of surface area of calcite. Because even after the experiment, we still found a good amount of calcite in the sediments. So we interpret that this is due to the surface area and reaction contact surface. After CO2 stops, calcium concentration drops very quickly to the background level. The second pattern includes magnesium, zinc, barium, and strontium, which is the metal concentration increases very quickly and drop back to the baseline with a few days. We interpret the mechanism of this pattern is dolomite dissolution because magnesium shows the most significant trend of this pattern, and dolomite is the major source of magnesium. The concentration drops to the baseline. We interpret that it's because dolomite is a trace mineral in the sediment, and it is likely to be expired. But it is also due to the loss of surface area because with the 3-day stop flow, we can see a little small peak of the magnesium release. So when we extend the interactive time, it might still have some reactions. And the third pattern is a combination of the first two. For example, uranium and manganese. The concentration increases very quickly and drop to a higher level compared to the baseline and keep stable till the end of CO2 injection. We also interpret that this is a combination of the first two mechanisms, including dolomite dissolution and or cation exchange and adsorption. And the later stage is more due to calcite dissolution and its impurity. To verify our interpretation of cation release mechanisms, we use simulations. Results show a very good match for the concentration changes. We also calibrated the parameters of these reactions. To better understand the concentration peaks in the first few days, we tried different combinations of mechanisms, including dolomite dissolution, cation exchange, and adsorption. We found that dolomite dissolution as well as cation exchange are two key mechanisms of the concentration peaks in the first few days. Here in the simulations, we use zinc and manganese as examples. So here are some conclusions from this study. CO2-rich synthetic groundwater intrusion leads to dolomite and calcite dissolution to release cations. Interpreted mechanisms of cation release are dominated by impurity of dissolved carbonate minerals. To be noticed that concentration of manganese in effluent shows a notable increase of about 100 times of baseline and exceeds Environmental Protection Agency's secondary maximum contaminant level, which might become a groundwater quality concern if there's any CO2 leakage into the Ogallala aquifer. So broader implications including providing information for further longer-term risk assessment and as well as for generalized studies of clastic aquifers and reactive transport of trace metals from groundwater sediments. This study is published in Water Resources Research. So if you are interested in this study, you can find more details online. Very importantly, I would like to acknowledge the funding from the U.S. Department of Energy and National Energy Technology Laboratory. I also want to acknowledge my co-authors, colleagues, and collaborators for the study, Dr. Brian McPherson, Mr. Rich Esser, Dr. Wei Jia, and Dr. Zhen Xuedai. Thank you very much for listening. And if you are interested in publishing some of your research of geologic CO2 sequestration, please have a look at this special issue. If you have any questions about the special issue as well as this presentation, please feel free to contact me. Thank you.
Very much, Xiao, for your presentation. Do we have any questions? Anyone from the studio?
I have a question, but maybe it's because I've not dealt with data like this before. I see in all your results, when you stop the injection of the CO2 and go back to the nitrogen, it kind of looks like it returns to like normal, but not quite. So do you think that there is like maybe something still stuck in the rock, some CO2 stuck in the rock, or do you think that's just like within the error bounds of your measuring techniques?
I think it's very sensitive of the testing technique of ICP-MS. So I also kind of struggling with the after CO2 intrusion. It's not like as quick as I thought, especially pH. It's like more about 1 week to approaching to the baseline value. So I think it's just a time issue of go back to normal. So even after CO2 leakage is stopped, we still need to take care of the groundwater quality for another while to make sure it's go back.
Okay, thank you.
Thank you. We have an additional question from the audience here. So Nara Brandão asks, could you say again, why did you stop the injection for 3 days, please?
I want to extend the hydraulic retention time to make it longer interaction between CO2 and the sediments. Is that clear?
Right, yes, I think so. Super, so do we have any other questions?
Yes, I might have one more question. As you're sort of dissolving your rock away, do you think that it will also have an effect on the geomechanical properties of your rock?
I believe so, but because we collected it in the Ogallala aquifer, it's more like a sand, not a rock. So it's hard to test the mechanical changes. But yes, I believe with the CO2 interaction, there must be some mechanical changes. And my colleagues did some similar tests and experiments. Yeah, and they found some changes.
Okay, thank you.
So if there are no other questions, I would say we finish here. And we thank again both our speakers, Ting Xiao for the presentation now, and Olivier Vincent from the one from before. Thank you very much for everyone. And we get back again on 2 weeks from now, and we will have presentations from Leila Hashimi from Delft University of Technology in the Netherlands and Tayo Akindipi from the University of Wyoming in the United States. So that's the next session on 5th of October at 3 o'clock Central European Summer Time. So thank you very much once again. Stay tuned, and we'll see you again 2 weeks from now. Bye-bye.
See you. Bye-bye.
Goodbye.